My name is Julia Brodsky, and I lead the Art of Inquiry Space Science School for the kids. And this summer we are hosting free webinars for kids on space sciences. So today I would like to introduce Dr. Adrian Lenardic. He is a professor of Rice University. He studies astrobiology. He loves astrophotography. In fact, his first degree was in art, right? And he also loves skateboarding. So yes, cool, Sheila, right? So before we start, I just want to remind you about our rules. Since there are so many people participating in this seminar, I would ask you to keep your cameras and microphones off, right? But please feel free to ask your questions in chat. Ask your question only once. Please don't repeat your question again and again, right? Because this way, I will be able to follow all the questions. Please don't spam in chat, even if you feel so, right? Please don't police each other. We have a co-host and moderator to do that. Okay, so now you know the rules and let us start. So I will stop sharing my screen and Dr. Lenardic will be able to share his.
I will start sharing my screen. Okay, as Julia said, I am in Houston, Texas. I teach at Rice University and I teach planetary science, but I've also had the good fortune, luck, opportunity, however one might want to say it, to teach in our arts department. I co-teach in a photography class. And I thought I would start our thinking out by showing an image from that class, from a student project. And this seems like a nice one to me because this is a view, not exactly this view, but something close to it, that all of us could have. We don't need fancy telescopes. We don't need unfancy telescopes for that matter. We don't need rocket ships. We can all go out and look at the stars and see them. The other reason I wanted to start with a photo with photography is because when photography started, early in the days, it was actually called painting with light. And that's a beautiful expression. And photography is all about light. And one of the things I want to get us thinking about, maybe even be amazed by, I'm still amazed by it, is how much we as people, curious people, how much information we've extracted just from light. If you want to take photos like this, and I encourage you to, go out and experiment yourself. Your cameras on your phone will work. If you have an actual camera that you can adjust, it might be a little bit better. If you want to take a photo like this, you're going to need a little bit of patience because astrophotography, you have to leave the shutter on the camera open for a while. And the shutter is the part that opens that lets light come in. And the light goes onto a sensor and the sensor registers it. The stars are bright, but they're not that bright relatively. So you need a long time to expose it. So that's that patience. And Matthew had to hold his camera for about a minute, which is pretty cool. And he actually did it without a tripod. So go out and play, make a science teacher happy. If nothing else, go out and take some photos of the stars tonight. Here's another view you can get. This is also from a project we did in class. It's the moon. You can look at the moon. If you haven't looked in the moon in a while, go have a look. This is the moon taken at an interesting time. This is actually at a lunar eclipse. Now, a lunar eclipse occurs when the sun, the earth, and the moon line up in such a way that the moon goes into the shadow of the earth. And that's an eclipse, and it should go dark. Now, I know you're looking at this image going, well, wait a minute, Adrian, this is either before or after the eclipse. It's not. It's during the eclipse. And now here's a question to you. If the moon is now in the shadow of the Earth, why are we seeing it as reddish? If we were together in person, we'd have an open chat about this. I'd ask you all. Zoom does have a chat feature, so let's take a heartbeat. Breathe in, breathe out. Write down what you think the answer might be. If you don't know, that's cool. I mean, just asking the question is a good one. If you're watching this with some friends, maybe some parents or grandparents, maybe you can tell them what you think the answer is and see if they know. As you're thinking about it, let me give you another thought question, if you like. Imagine this. Imagine you're an astronaut and you're in your rocket ship and you're about to leave the Earth. You're about to go into space. Do you think you're in space right at the point that the rocket ship leaves the Earth? When are you in space? Another way of saying that is, what is the Earth? It's not just the solid part. There is also what we call the atmosphere. And the atmosphere is an outer envelope of gases that are held on our planet by gravity. And the reason you're seeing the moon as slightly red here is because of the Earth's atmosphere. And if you didn't know that, that's fine. If you had ideas otherwise, that's fine too. But what's happening is the light of the sun, it is being blocked by the solid planet, but some of it is going through our atmosphere. And that light is interacting with the particles in the atmosphere. Some of the colors in the light from the sun are being absorbed by certain particles. Maybe we all heard about the rainbow, red, orange, yellow, blue, green, indigo, violet. I've memorized that as a kid as Roy G. Biv. But the blue components are being taken out. Also what's happening is light is being bent as it goes through the atmosphere. For those of us who wear glasses, it's how a lens works. And that bent light going through the Earth's atmosphere is then hitting the moon. And we're seeing, by the light, the Earth's atmosphere on the moon. And the color of the moon is telling us something about the Earth's atmosphere. Keep that in mind. As we look for life on other planets, the atmosphere is going to be crucial. The next image I'm going to show you is one that all of us can't take on our own. It's not a photo we can take, but we can all view the photo. We can all see it. It's a photo that has a strong connection to the city I live in, Houston, the space city. This is a photo taken from a NASA mission, Apollo 17, on its way to the moon. And this was in 1972. And as we were going to the moon, and anytime I say we, I mean all of us collectively as curious human beings, the astronauts turned around and took this image of our own planet. This is referred to as the blue marble image. It's stunning, it's beautiful, it's one of the greatest photographs in the history of photography. Now, 1972 to some of us might seem like a long time ago, but relative to the amount of time we as people have been around, that's not that long a time. And this was the first time, the very first time, we could see our planet this way. We had never seen it this way. We thought about it, we speculated, but this view, and this is an actual photograph, there's no touch-ups, nothing, the first time. It's sometimes hard to think about that for those of us who grew up with this image, but it just changed our entire conception of the planet. Something else that's interesting, this is one of the most downloaded images off the World Wide Web to this very day. It's iconic, and it's beautiful. Some of you might know that we have a space station. Again, we as people. Astronauts were supposed to go there this week. There was a bit of a weather problem, but hopefully it will happen over the weekend. And this is an image an astronaut took, again, a photograph from the space station, and you can see all the stars, and you might see a concentration of stars along the center. And this is a view of our galaxy, the Milky Way galaxy. And galaxies are collections of stars. And a little bit of history here. We've been looking at the night sky before we had photography. And one of the earliest ways we registered it is artists, painters, would go to observatories, chat with scientists, look through the telescope, and then paint what they saw. And this is a painting of our galaxy, the Milky Way galaxy, in 1874, before cameras were around. And you can see this beautiful image. We now know within a galaxy, a lot of the stars we're seeing have planets orbiting them. These are referred to as exoplanets. Now, Julia has told me that you've had a discussion about exoplanets, so you can go back and look and see how we find these. But again, this certainly is something we didn't know about directly until really maybe 10, 20 years ago. Now, again, that might seem like a long time for some of us. For the parents and grandparents, maybe not that long. It's relatively recent. We thought they might be there, but we had never really detected them. And now we're finding them. And the thing is, we're finding a lot of them. This is from NASA. NASA updates daily. They update daily on the planets we found around other stars. So I pulled this up a couple of days ago for you, and you can see we got about 4,000. That's pretty cool. It's a fair amount. And the amount of stars we think are in our galaxy is about 100 billion. Now that's a hard number to get one's head around. I mean, it's a lot. And we're finding more and more of these planets around those stars. Now, speaking of some of the greatest scientific photography in the history, this is one of those. This is referred to as the Hubble Deep Field View. Some of you might know that Hubble is a space telescope. It's a telescope we put up in space. It's actually not that far from the Earth. The reason we put it up in space is to avoid interference from light sources we have in cities, so we could actually have a better view. Everything you're seeing here, all those bright blues and oranges, those are other galaxies. Now let's think about that for a minute. Other galaxies like the Milky Way. Remember, our galaxy has about 100 billion stars. These are other galaxies. We estimate, and it's an estimate still, and we're learning more, that the universe, all the stuff we can see, has about 2 trillion galaxies in it. That's crazy. Remember when I told you that Matthew's photo of the stars required a little bit of patience? So did this one. Hubble, this image, Hubble had to actually expose. So it had to keep its shutter open to let all the light hit the sensor for 22 days. 22 days to get this incredible deep field view. I am hoping at this stage, you, like me, are asking questions. And I see chat, and I hope the chat has questions. I wish I could, question along with you, but we'll get there. Think about all those galaxies. Within all those galaxies are all those stars. Many of those stars, more and more, have planets around them. It kind of makes you wonder. Now, I know what it makes me wonder about, but again, let's take a minute. Breathe in, breathe out. What does it make you wonder about? And again, some of this wonder can come from us looking, from photos you could take. Others require we might pull the photos down, but I will tell you, in putting together my little slideshow, I made sure that almost all the images I'm showing you are easily accessible through the internet. What do you wonder about? Something I wonder about, maybe some of you wondered about it. Is there life beyond Earth? Now, I don't know this for a fact, but I suspect that the first time somebody like ourselves, some human, actually looked up at the stars and was in a position to talk to other humans, this might have been one of the first scientific questions we asked as people. It's just hard not to. You see all those stars. Again, take a minute. What do you think? What do you think the odds are? Do you think there's other life out there? Now we can think about those things and we can use artistic responses, we can use gut feelings, we can use all sorts of things. As humans, we can think a multitude of ways. From art to science, we can do both. The thing is, though, when we put on our science hats, and we all can, and we decide to answer a question, what will make that scientific is if there are some observations we can use, something we can point to that says this provides an answer to that question, something beyond a gut feeling, something that is independent of us in the sense of, oh, I find this pretty, I find that pretty, something that is direct evidence that we can all share and all agree upon. So if we want to answer this in a scientific way, we got to think about this. How would we find it? How would we detect it? What would we observe? Now again, think about that on your own. Maybe we could go to the planet, but the thing is, right, a lot of the planets around all these other stars are very far away. We won't be able to travel there. The nearest star to us is Alpha Centauri, and it's about 40, ready for the big number, trillion kilometers away. It's just that far. Which means that these sort of science fiction views, and by the way, I love science fiction. I think it's great. From reading science fiction to movies about science fiction. And this is from a movie, a somewhat old one, but I find it a beautiful still. Searching this way is going to just take a long, long time. We won't be able to do it. It's just too far, particularly for stars distant from us that might have planets. And that's where most of the planets we're finding are. We can do it with big telescopes, and we do that. And that's what I'm going to talk about for the most part, looking up at the sky. But then there's this question of what is it we'll actually look for? What is the signal? It's taken me a while to get to the title of my talk, but this is the title, Life Beyond and on Earth. You had a talk on SETI, I know that, the search for extraterrestrial intelligence. And when astrobiologists use the word intelligent, which is a kind of loaded word, it can mean many things, we generally mean a life form that can actually send signals across space. And we've been looking at that for a while. I'm not going to talk so much about that. You can actually look at the videos that Julia has recorded. I'm going to think about what if the planet has a life that hasn't progressed to the point that it can send signals of some sort. So maybe plants, animals, bacteria, things like that. What would we do? How could we detect that? This is where we meet the first of three really interesting human beings and scientists I want us to think about. This is James Lovelock. And he's sitting with one of his early creations. James Lovelock was essentially, early on in life, an inventor. He made gadgets. And what's kind of cool is he made a lot of the gadgets in his barn in England. He wasn't actually working at a university or an institution or anything like that. He was just kind of curious and he was good at it. He made one of the first instruments that could actually detect levels of ozone in our atmosphere. And that's oxygen, it's O3, it's different than what we breathe. But some of you might know that ozone in our atmosphere protects us from damaging ultraviolet light from our star. And there's not a lot of it there, but he was clever enough to make an instrument that could detect low levels of it. This is what got him noticed by NASA, because NASA, and this is now in the 70s, was thinking about going to Mars to look for life on Mars. And they already figured it's not going to be the type of life that comes up to you and says, hello, Adrian, or hello, Julie, that it might be bacteria, fungus, things like that. And they wanted an instrument to detect it. So they brought in James Lovelock. And they said, look, you're good at gadgets. Create us a gadget to find life on Mars. And again, you can think about it yourselves, right? Imagine you're James Lovelock. What do you do? What are you thinking about? What do we make? And Lovelock thought about it. What's interesting here about Lovelock is, and I'll give you a little teaser, he was going to tell NASA something they didn't want to hear. Now, the thing is, in science, right, remember, evidence, just because we don't like something, if that's what the evidence shows us, well, that's what we got to accept. In pondering this question, he started thinking about it in a more general way. He said, well, let me think about it first this way. What if I actually couldn't even go to Mars? Could I try to address this question? And he started thinking about, ready? Atmospheres, atmospheres, atmospheres. And he knew that we already knew something about our atmosphere. Hopefully all of us have learned that early on in school. The thing is, at the time, we also knew something about the atmosphere of Mars and actually the atmosphere of Venus. We had sent remote probes. So these three planets, Venus, Earth, Mars, all in our solar system. Sizes here aren't to scale, just so you know. Venus is about the same size as the Earth. Mars is considerably smaller, but I've blown it up a little bit so we can see it. And this is the way we would see it from telescopes. And you know, this is the way we saw the Earth from Apollo 17. Here's what else we knew. Now I'm going to show you something that's a bit of a graph look, not an image. But we knew something about the compositions. For those of you who haven't seen information presented this way, what it shows is relative amounts of stuff. And this is the relative amounts of stuff in the atmosphere of Venus, Earth, and Mars. And relatively, the atmosphere of Venus is mostly CO2, that's carbon dioxide. And you see some nitrogen. The clouds of Venus are actually sulfur clouds. You know, the clouds on our planet are water clouds. So Venus is different in that regard. We go to the center, the Earth, and you know, this is one I learned, I think, in grade school. Hopefully we're still learning it then. Our atmosphere is mostly nitrogen. There's oxygen, water vapor. That's what makes clouds, the rain, the snow. Some other small stuff. And there's a lot of other small stuff, ozone not here. And then we look at Mars and we see again CO2. When I came to this country, I couldn't start school right away because I didn't speak English. But my mom actually helped me learn, and my grandparents helped me learn. And I would watch a little bit of TV to actually learn English. And there was a show on then, and I don't know how many of you will remember it, but it was called Sesame Street. And it was a TV show that would actually provide some learning content for kids. And it was a great way for me to learn English before I could actually start kindergarten. There's a game that was always played on Sesame Street, and it went like this. They would show you a few things, and then they would say, I'm not going to sing it. I have an awful singing voice, but it would be done in song. One of these things is not like the others. This is the only pop quiz I'm giving you today. So write it down. Which one is not like the others? Yeah, you can write it in chat. Don't worry, you all get A's. It's fine. Hopefully you're noticing something. The Earth, remember this, the Earth's atmosphere stands out. Let's put ourselves in James Lovelock's shoes. I find this kind of a nice thing to do as a scientist, and just in general as a curious person. As I read about the history of science, sometimes I'll stop and just say, well, wait a minute, before I read, let me pretend I'm this person and I'm confronted with this question, what do I do? This is what Lovelock had to do. Why is the Earth the oddball? So again, let's take a minute. What do you think? What could it be? Now remember, Lovelock was hired by NASA because NASA was convinced there was a chance that there was life on Mars, so much so they were going to send a spacecraft there. He was about to tell them, I'm sorry, you're wasting your time. I can tell you from the atmosphere, there's no life on Mars. Because his answer to this question, why is the Earth's atmosphere the oddball, was because the Earth has life. It has life that's interacting with the atmosphere. NASA still went to Mars. They dug stuff up. They found no evidence of life. We're still going and looking, maybe for ancient life, but we haven't found it. Lovelock was correct. And think about how he did it. Through the atmosphere. And remember, we can get information about the atmosphere without going to the planet. Remember, looking at the moon gave us information about our own atmosphere. Kind of crazy. Life. And Lovelock reasoned this way. We know that life at the surface of our planet depends on the atmosphere. We know that directly. We need it. It's what we breathe. That's why we're so worried about keeping our atmosphere clean. I've heard this analogy that literally we and all living things that share this planet with us at the surface swim in a sea of atmosphere. But what people hadn't thought as hard about until Lovelock came in and actually started thinking about life on other planets was that not only is life on this planet dependent on the atmosphere, it is changing the atmosphere. And it is changing it in a noticeable way, a very specific way, making it look like something very different than any other planet that doesn't have life. That was Lovelock's idea. Now he pushed it. He said, well, wait a minute, if life is affecting things this much, maybe we can't just think about life responding to the environment. Maybe we need to start thinking about life, ready for the different word, interacting with the environment. James Lovelock was not a biologist, and biology is principally the study of life. As I told you, he was an inventor. Here's a nice lesson I learned from what Lovelock did. When he didn't know something, he decided to ask somebody who did. And he contacted a colleague, the second interesting human being I certainly want to introduce us to. He went and contacted Lynn Margulis. Lynn Margulis is a biologist. She was a biologist, unfortunately. She passed away recently. And she was very famous for an idea she had. And Lovelock knew, I need to get a hold of this person because this is really interesting. Now, the idea was symbiosis. And I don't know if everybody's heard that word before. Think about it. Maybe your parents or grandparents, or maybe you yourself have heard, sometimes we hear this phrase, symbiotic relationship. Symbiotic, that means you get something from somebody, they get something from you, and 1 + 1 in some sense is more than 2, right? Because you're interacting with each other. And Lynn Margulis's idea about symbiosis for the Earth was that early on, 2 simple life forms, bacteria, actually started working together to become more complex. And that this was a key step in evolution in the path from bacteria to quite literally us. It's a famous idea. Lovelock brought her in to say, okay, let's think about how life forms, not necessarily as complex as us, right? I mean, obviously we change the atmosphere through commercial ways, things like that. But he was wondering more just basic life living its thing. And they got together and they worked things out. And it led to a pretty famous idea. I think this is one of the more influential scientific theories to come out, certainly in my lifetime. So within the last, 40, 50 years, I shouldn't give my age, but his idea was called this. It was called Gaia, and you pronounce that Gaia. And the idea he put forward, and you can get this book, I think some places you can actually freely download it. And I will tell you, James Lovelock is a very good writer. He's very effective at condensing what can be sometimes complex ideas into something very simple. And the idea here was that not only does life depend on the environment, it interacts with it in a particular way that can maintain life itself. That was the idea. To give you a little bit of sense that James Lovelock is an effective communicator, the name of this theory was suggested to him by one of his neighbors. Now, I mentioned to you that Lovelock lived in England, and he did. He lived in a very pastoral area in a barn where he'd make stuff. In fact, making stuff made him money, so he could actually think about science. He was walking with his neighbor, William Golding. Now, some of you have heard of William Golding. If not, I'll tell you in a bit. And he explained his idea to William Golding. And Golding said, you know what you got to call this, James? You got to call it Gaia. And Gaia is after a Greek goddess, a Greek mother goddess, that is associated with interactions, with things working together. If you haven't heard of James Golding, he's a writer. He's most famous for writing a book, Lord of the Flies. And just to give you a sense that Lovelock appreciates a cleverly turned phrase, effective communication, hopefully that does. So I encourage you to track down his book. Lynn Margulis also wrote some of these ideas up in what she called the symbiotic planet. This idea has gained traction. It's now in schools. The most simple way I can say it is that life and the environment aren't isolated. That really connections define a living planet. And we're interested in those connections. That helped us understand our own planet. But remember, Lovelock was thinking about other planets. And this idea has come back to us in now moving toward my field, how we're thinking about detecting life on planets far away. So again, the Gaia hypothesis, the Earth is more than just a home, it's a living system. We're part of it. The fact the Earth's alive, the fact there is life can be seen in its atmosphere. We can detect it through the atmosphere. Think on that. Back to those questions. Is there life beyond Earth? Second question, let's make this science. How do we detect it? How do we do it for planets that we can't get to? The science jargon word here is, can we remotely sense it? But we can see it. We can see it through the light. Again, the Earth. Here's another view of the Earth. This is the third interesting scientist I want us to meet. Now, this is not a pretty looking picture. I understand that. What are you going to do? It was a hard picture to take. This is a picture of our planet. It's not called the blue marble. It's called the pale blue dot. And you see that little pale blue? You know what? That's us. That's the Earth. This was taken by a NASA mission Voyager, which was going out to Jupiter to look at Jupiter, a gas giant in our solar system. The distance it was away from the Earth is about 4 billion miles. And the camera was not designed to do this. The person who convinced the engineers, the people who run the gadgets, to do this was somebody called Carl Sagan. Now, maybe you've heard of Carl Sagan. He was a working scientist. He had a show, Nova, for a long time, where he introduced scientific ideas to all of us, all humanity, in ways we could all understand it. Here's an interesting serendipity. He was married to Lynn Margulis. They were husband and wife, powerful science team. He said to the engineers, can you do me a favor? Can you turn the camera around and take a picture of our own planet? Since I'm giving you a little bit of photography, the engineers thought, Carl, you are absolutely crazy, because we're turning the camera around into, ready for it, the sun. which is a really powerful light source. And they didn't know if that was actually going to blow the camera out. And it didn't. And he got this image. Keep that in mind. Go to the lights, young Jedi. For those of you who don't know Star Wars, this is from a science fiction movie, Star Wars. It's the earliest one. It's the one I saw as a kid with Obi-Wan Kenobi. I tell this to my students from introductory level to graduate student level, go to the light. What we extract from the light, the information we get from the light is crazy. And Carl Sagan knew this. That's why he wanted to turn that camera around. Because what he wanted to do is to say, look, the particular color we're going to see from the Earth, we can pick that apart. He wasn't sure, but he thought we could. And can we pick it apart from this distance to tell us what's in the Earth's atmosphere? Because it's the Earth, we already know. That's what he wanted us to do. That's what he was thinking about. Fancy science word. Hopefully I've kept it down to maybe a handful. Spectroscopy. Spectroscopy has to do with how we get information from light. And just look around wherever you are. You'll notice things have different colors. I'm in my office. I got a chair that's red, one that's black. They're all being illuminated by the same light source. It's coming from the sun, but they all look different colors. And the different colors is not due to the different light source. It's actually due to the material. So the material reflects the light in different ways back to our eyes. And the color that comes back to us gives us information about the material. Now, colors are the simplest ones, but there's fancier ones. Originally, spectroscopy started when somebody was sitting in a room really distant from a fire. And they said, I wonder if the color of the fire is telling me what's burning. And we figured it out, that we could do it. Then a very clever woman said, hey, I wonder if the color of the sun is telling us something about what the sun is made of. And lo and behold, we could do it. Spectroscopy. The second kind of a little bit more technical type graph. So what are we looking at? If we look at the Earth from a distance, and we look at the light that's coming to us, let's say from that Voyager mission, the difference between a planet and a star is that planets don't generate their own light. We see planets light because sunlight hits them and then reflects back. But as it hits them, it interacts with the atmosphere. Remember the moon. Remember the moon. That was light coming from the sun that had gone through our atmosphere and it had been changed in a particular way. That's why it appeared red. What we're seeing here, the little jiggly, jaggedy bands. Notice where it goes low. There's a particular component of light we're not seeing, which is giving us information about what's absorbing that wavelength. Again, remember Roy G. Biv, red, orange, yellow. These are different components, different wavelengths. So we can see what are called these absorption bands, that we actually see water. O3, that's ozone. Remember James Lovelock, ozone, CO2. So we can get that information about the atmosphere of the planets. This is how we are looking for, or going to. Hey, by the way, we haven't really started this yet. It's coming. You'll all get to watch it play out. The hope is to use, the thought is to use spectroscopy to get at what we're going to call biosignatures. Again, remember what Lovelock said about Mars. Remember now we can actually detect what's in the atmosphere of distant planets if we find particular combinations of molecules that are signatures of life at the surface, just like our own planet versus Mars versus Venus is signature of a living planet. That's a way we'll be able to say, okay, this planet looks like it has life at the surface, altering the atmosphere in a particular way. Crazy, but there you go. Sagan foresaw that. That's why he said, let's make sure we can do this. That's why he wanted to test it out. Sagan and Lynn Margulis thought about it. Really what we're doing in honor of Lynn Margulis who is just a really fascinating person to read about, and you really should if you can. We're going to look for symbiosis from space. We're going to look for interaction of life with the atmosphere from a big distance. And I think we're going to find it. I hope so. Now, we don't know until we go. But again, in this atmosphere, in this solar system, we know we can do it. We have done it. We've tested it out. Scientists can be sometimes annoying by really just saying, well, are you sure? Are you sure? Are you sure? Are you sure? There's a famous quote by Carl Sagan that I remember related to this. Big claims demand big evidence. And if we're going to say there's life on another planet, I can't think of a bigger claim I could make. We want big evidence. That's why we've been testing this out so much, so much. The pale blue dot. Here it comes, a photograph, one of the first ones of planets around stars other than our own. Okay, it's not as pretty, Adrian. I know it's not, but this is a long ways away. You see the little bluish things around there? Those are planets. They're orbiting another star. Now, the star, that black, the light of the star has been blacked out in this image, because if we didn't, it would be so bright we wouldn't see the planets. So that little star in the center there is representing where it is. And we're seeing these planets. And we're gearing up to do spectroscopy to say what's in the atmosphere. Pardon me. The image I showed you actually came from ground-based telescopes. This is the ALMA array. It sits in Chile. Big plateau that's actually pretty high up in the atmosphere. And it's away from city lights. That's really what they're trying to do. And, you know, if you're interested in this, you can private message me and I can give Julia my email on how this works. But the simple description here is that by linking these small telescopes together and getting them to communicate with each other, we can make it look like a much bigger telescope so we can see further. That's the idea. Eventually, we're going to go further than that. We're going to go with space telescopes. This is a plan of missions that are coming. And I noticed in the SETI talk you had, this was shown as well. And it should be, because it's pretty cool. It's an international effort. It's not just NASA, it's the European Space Agency. Canada has a space agency, Japan. The one we're waiting for is James Webb Telescope, which should launch, I'm thinking, in a year. And there's another nice Houston connection. It actually resides here. My wife has a friend who actually is an engineer that works with the James Webb Telescope. She's gotten to see it. And we're going to send these up. And these missions now are designed specifically to look at the atmospheres of exoplanets. So far, we haven't really specifically designed missions to do that. And that's why I said this is coming. It's ongoing. And you'll notice one of them is named Gaia. That's kind of cool. So it's coming. Now, skeptic. Some of you might be thinking, well, yeah, but right, we're looking for life as we know it, right? Something at the surface, oxygen, those sort of things. Let me ask you this, any worries about that? And again, I'm giving you a heartbeat, think about it. If you're sitting with people, you can ask. Let me ask it another way. Another thing, us people who, you know, like to say big claims, big proof, we can be annoying this way too, because we always like to ask these questions. What could go wrong? What are we missing? And I see the chat going. Hopefully you had a chance to answer it on your own. What could happen? What could go wrong? What could go wrong? Well, it's an image of a lamppost and a person under the lamppost. Some of you might have heard this story that a friend finds another friend looking under a lamppost, asks, what are you doing? The friend says, I lost my keys. The other friend says, well, why are you looking here? They're clearly not here. The one person says, well, the light's the best here. Yeah, but maybe the keys are a little off in the dark. And maybe in looking for life as we know it, We're looking for the easiest thing. But what if there's something unexpected? How strange could extraterrestrial life be? Hey, I told you I'm a sci-fi fan. I love it. We've imagined all sorts of crazy things, haven't we? Sure. What if life isn't exactly what we think it is? Will we miss it? Now, if that's a question you were thinking, hey, good question for sure. We've been thinking about it as scientists. This is a really big, honking report. I don't recommend you read all of it. The Weird Life report, that's not actually on it, I added that. It's a group of scientists got together and started thinking, okay, let's imagine different forms of life, not exactly like ours, and then think about how we could detect that. And it was in some sense a call to NASA to say, okay, let's make sure we're trying to cover our bases. Maybe it's going to be different than we think. That's also ongoing. We're trying our best. We're working on it. Let me end with this, and then we can have some questions. This whole deal is, to me, a big adventure. It's one that starts from just looking up at the night sky and wondering. You can do that yourself. Go take some photos, have some fun with it, think about it. Looking at the moon. The fact that on our planet, the moon is so close to us, a lot of historians have said is the reason why we started space exploration, because the nearest place wasn't that far away. We thought, hey, that one's doable. Let's give it a shot. Might have been different if we didn't have a moon. We walked on the moon. Beautiful photo. The photographer I co-teach the class with, Jeff Winningham, says this is one of the greatest photos in human history. The astronauts were not professional photographers. They had a little bit of photography training. They went up, Kodachrome film. They took the images. Do you see the reflected image of the one photographer taking a picture of the other photographer, also known as astronauts? Amazing, just amazing. Apollo, 1972, the first view of our planet this way. Our thinking about our planet changed. Historians will say environmental movements, the desire to protect our planet, its atmosphere, really started with this image because it looks so delicate and so beautiful. To the Carl Sagan one. If we have time, I'll read you a quote from Carl Sagan about this. If not, we'll just open it for questions. Question to you. What's next? I'll let you think about that. I have an answer. I'll give you my answer and then I'll take some questions, and then if there aren't more questions, we can go on. You know what my answer is? Tell us, Adrian, tell us. You're next. The next steps are for you. What's going to happen is going to happen over your lifetimes, most of you. Watch it play out. I can stop and take some questions, or I can finish up a little bit. However you want to do it.
So do you want to hear the quote? Do you want to ask some questions first? Please share in chat. They want both.
They want both. Okay, but you got it. Ready? Now, why do I like this so much? Sometimes us science types can get stereotyped. Oh, Adrian, he's such a nerd. He's just a scientist. Oh, Carl Sagan. No. We're just curious people like everybody else. Here's what Carl Sagan, in what to me is very poetic and something that quite literally at times has teared me up when I read it. Here's what he said about this image. We succeeded in taking that picture from deep space. And if you look at it, you see a dot. That's here. That's home. That's us. On it, everyone you have ever heard of, every human being who ever lived, lived out their lives. The aggregate of all our joys and sorrows, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilizations, every king and peasant, every young couple in love, every hopeful child, every mother and father, every inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there on a mote of dust, suspended in a sunbeam. If you're not crying, you're not me. Well, maybe you're thinking of questions, I don't know. Well, maybe as Juliet gets the questions together, when I say it's you, here's you. It's kind of a cool thing. This is a selfie. I think people know what a selfie is. Yes? It's a selfie from NASA. You can't actually tell, but this is a composite of more than 36,000 photographs. And what NASA did is they said, everybody take a picture of yourself wherever you are, and then tag it as global selfie. And then NASA put them all together and made this photo mosaic. And you can download it. It's a huge file because you can actually start zooming in and seeing the people. And it comes from 113 different countries. It was all posted on Twitter, Instagram, Facebook, Google, Flickr, all these big platforms. And if you zoom in on it, you'll see a lot of the people. This is really kind of cool as us as a collective, symbiotic humans, are holding signs that say, "Hello, NASA." And it's just a wonderful thing. It's just really crazy to me.
So, Adrian, we actually have some wonderful questions here.
Cool.
So,
I'm ready to take them.
for example, what if there is not enough life yet to change a planet's atmosphere? Is there a threshold for that?
Good question. Yes, there is. Yes, there is. What Lovelock was thinking about was what we call kind of a global biosphere, where it's kind of taken off everywhere. If there is life in certain pockets, certain regions, let's say in caves or something like that, then you're right, we're going to have a hard time detecting it. We won't be able to detect it that way. And I'm going to be honest with you, that is the reality. We might miss some stuff in that regard. Excellent question. The threshold limits, those are changing every day. And why do I say that? Because this is ongoing work. This isn't stuff you're going to find in history books of science, because it's happening right now. That's why I'm doing it. The instruments are being developed and changed. And even over my lifetime in this field, those detection limits have changed from literally year to year. So one, I don't actually remember the detection limits, so sorry. The other one is why I'm not going to really present it now is it's going to change over time. But we do think about that, and the instruments clearly have certain detection limits. I think the safest way to say it is that we would be able to detect a global biosphere interacting with its atmosphere, so that there's life somewhere, everywhere. A local biosphere, probably not right now with the instruments I know of, but that's the way it is. We learn. We learn.
So another question is, right now it looks like we are looking only for biosignatures from carbon-based life. What would be the biosignatures of non-carbon-based life?
Excellent question. Excellent question. So the Weird Life report that I gave you a link to, and again, it's just a really tough read, so sorry. It thought about just that. And you've heard the phrase, we're a carbon-based life form. If you look where carbon sits on the periodic table, it's in a particular place. Now, why is carbon good for life? It can bond with a lot of other things. So we can actually have complicated stuff, and life is complicated. It also makes relatively strong bonds so they don't get ripped apart, so life is stable. If you go and look, go one down from carbon, you'll see silicon. And silicon also shares some of these properties. It can make all sorts of bonds and it can be strong. So people have started thinking about silicon-based life. And that's the one I know of that's getting some work done, and then asking the question, okay, if we had maybe silicon-based life, what types of biosignatures should we see? Also ongoing work. So this week, I told Julia, I had a Zoom conference, which was more on my professional science side, although all this stuff, right, can be condensed to anybody who's interested in it. That came out of University of Chicago, and one of the days was on just that, was on what are called exotic biosignatures, and we're thinking about that. One of the ways we're trying to test it out is actually in laboratory work, trying to actually, right, because if, you know, where do we see this type of life? We're trying to actually look at what are called extremophiles. So even on this planet, there are critters that live in conditions we used to think nothing could live. Like at really high temperatures, we started finding them even on this planet, or under extremely acidic conditions. So these extremophiles are giving us a way to start thinking about life forms and what they might look like on other planets. So that's how it's being done at present. But you're right, the first generation, the first telescopes, James Webb, it's going to focus on carbon-based life. Now, we can say some things might go wrong, they might, but the thinking is our best odds, our best chances are detecting life as we know it. And if we find that cool, if we don't, then we'll go back and rethink. But that is how it's going to play out, and you're quite right.
Another question is, what planets are we going to next?
Good question. Good question. So within this solar system, you know, we're all over Mars. We have rovers there. I have colleagues who do it. We're still there. One of the coolest new missions that's coming is actually not to a planet. It's to a moon in our solar system. It's a moon of Saturn. It's called Titan. The name of the mission, I love this, it's called Dragonfly. Actually, a friend of mine is leading the mission, Zibby Turtle. She's really clever scientist, generating the interest in this. Here's why it's called Dragonfly. What's going to happen is we're going to have drones, and some of you might know drones, these little helicopters. The spacecraft's going to go to Titan. Now, Titan has an atmosphere. We've measured Titan's atmosphere. We're not sure if there's life there. We don't think so. But there are molecules that seem to be what's called organic chemistry. There's carbon there. So they're going to drop off a bunch of these little helicopter things that look like dragonflies. And they're going to fly around the surface of this moon to actually make measurements, recordings. And Titan is, man, you know, I told you I like sci-fi. Man, it's something that I would have thought would be sci-fi. But yet there it is. There are lakes on Titan. They're not water lakes. They're hydrocarbon lakes. That's like oil and stuff. So they also want to get measurements there. The thought is that Titan might be like a planet that doesn't have life yet, but maybe has all the right ingredients for life. That's the next one. There might also be a mission to another moon that's pretty cool. It's a moon of Jupiter, Europa, and now it has an ice shell, but we have very good evidence that below that ice shell is a submerged liquid water ocean. And gosh, I'm blanking on the name. Stephanie's going to kill me. I'm blanking on her last name, but the lead scientist of this is from Georgia Tech. And what she is proposing to do is to drill through this ice and then put a little submarine under it, and then go through this liquid ocean water and see if we detect life. The way they're answering these skeptical science questions, you know, can we do this, can we not? That submarine is actually being tested out in Antarctica right now. It's actually below the ice in Antarctica, moving around. Those are the two from the astrobiology side that I think are pretty cool and pretty interesting. We might also go back to Venus down the road. The surface of Venus is 450 degrees hotter than it is here. And we don't think it's conducive to life, but we do wonder, maybe in the past things were different, and there are ideas for that. Those are the ones that are pretty sure. The Titan one's going to happen. Mars is happening. Europa, I think it's still in, what a scientist called the test phase, making sure it's possible. And we just had a really successful mission to Pluto. And Pluto looked completely different than we thought it would. And I tell students this, if there's one thing I've learned, and I'm glad to see your questions about silicon and all that, be prepared for surprise. That's why we explore.
Okay, it looks like we're actually at the end of our lecture today.
Cool.
So,
if you have other questions, contact Julia. I'm happy to take emails. If I can't answer your question, maybe I can give you a link.
thank you. Thank you so much. And if you could put this presentation somewhere on your website, I would be able to
Sure.
direct people to it.
I can do that. And okay, well, I didn't get the question I was hoping I'd get.
Which one?
I'll end here with a little quote from a poet. And just remind us that, the title Beyond and On Earth, really what I find interesting, I find many things interesting, hopefully you do too, is how much we've learned about our own planet in thinking about exploring other planets. The question I didn't get is, do you really skateboard? Well, yeah, I do. So there you go.
Yes, this is a bonus.
Yeah. All right, I'm going to stop sharing my screen. And thanks all for listening. And hey, I hope you had fun and go out and, make a science teacher's heart tick-tock a little bit and take some photos yourself. Make a hoverboard. Yeah, well, dragonfly is a little bit hoverboardy. That's true. Yeah, those of you interested in that, I'll give you some links. There's some skate science stuff if you want to play with that, but it's not astrobiology.
People were talking about dry ice hoverboard on Mars.
Yeah.
I've heard of that.
Yeah, and I just saw a talk on not exactly terraforming Mars. So what the term terraforming means is changing a planet environmentally, and so maybe that it could be livable. Mars isn't that hospitable, but there are talks about how we could actually make camps and things like that could actually be maintained at livable conditions so that astronauts could go and colonize progressively. There has been talk about altering the entire atmosphere. I think that's way down the road. I don't think that's possible. But different materials that insulate and that move us around. Yeah, so that talk is there. It's been there for a while. Similarly from the moon, great sci-fi shows in the past about colonies on the moon and things like that. And how we get around on a planet, that's one of the things for exploration on this planet that has changed. And that's why dragonflies. So, we actually want to get to the planet and then have instruments that can move around it. Because a lot of times, right, if we can only land, we're going to land in a very safe place, right, where the ship won't break and things like that. So we don't get full coverage of the planet. So things like, hoverboards, as sci-fi as it sounds, no, it's actually not. We aren't thinking about that, how we can actually move around and dig deeper as well, drill through ice, those sort of things.
There is probably one last question one
Sure.
person really wants to ask it.
Sure.
What are the chances that aliens look like people?
Ha! Wow, what a good question. What a good question. I suspect, and it is chances, the odds are highest that the first types of life we find will not look like us. It might look like something on this planet, but likely not us. And a lot of that comes from thinking about evolution and progress along the way. And even over the lifetime of this planet, when there has been life, if we think about what percentage of that would look like us, that I would shake hands with at some level, it's low. And when we explore these other planets, they were going to be across an age range. They might not all be the same age as our planet is. So evolution might not have progressed as far. Now, since you ask, and why not, let's talk sci-fi. What if it actually progressed further? Will humans look like humans in 1 billion years? That's a good question. I don't know. It's an interesting one. And somebody said no. Yeah, well, it could be. This also gets into certain debates about life. So you said silicon-based life. Some people will say, and maybe some of you have heard this, the artificial intelligence debate. Could computers effectively become something that we call alive? Or could humans start to change in a way that they have a lot of attachments? And you see, Julie and I have glasses. I mean, we've been making attachments forever. But now it's gotten a little bit more sophisticated from what's called nanotechnology, that sometimes, things can be injected into bloodstreams, little machines, and fun to think about, fun to think about. I can't hear you, Julie. Julie, I think
Sorry, I forgot to unmute myself. Yeah. So another question was, have you ever been to space?
I have not been to space, no. I had a friend, Maya Tolstoy, who was in the astronaut program, and she was almost cleared. This would have been the closest. She did training in Russia at the time, and this is when most of the launches were coming from Russia. And then the program was pulled, unfortunately, so she didn't get to fly. I've met some astronauts, and Houston has them, and they give some interesting talks. I've met people who've been to the space station. One of the most interesting questions I heard of the astronaut who was at the space station was, well, when you get into the space station, does it have the smell of a new car or something like that? So these real world things. No, I have not. I'm probably past the age, so NASA has a lot of intensive training for people that go into space. A lot of it's physical, to make sure you're physically fit, mentally fit, those sort of things. So no. Would I go? Good question. I can ask you guys too. If you had the opportunity, would you go or not?
You are getting one more question about
Sure.
The merge of AI and humans. Can we genetically engineer humans and computers together to create superhumans?
Well, here's my simple answer. I do not know. I do not know. I do not know. I don't think that's being thought about scientifically by anybody at present. I know it's, sci-fi movies, and that's cool. There is a bit of a difference. Scientifically, no, it's not being thought about. The closest that is being thought about is aspects of nanotechnology to help our health. So things that, little machines that can actually make us live longer, maybe live better. There's, some of these glasses extensions with computers in them that can actually give us a bigger memory access, that we can actually, sort of quickly access the web. Whether our minds, are ready for that at present, I don't know. I don't know. I don't think it's an idea that's really being considered from the scientific side at the level you're asking it, but at the level of enhancements to ourselves, which you might call enhanced humans. That is, and it's actually not so different from many of the things we've been doing progressively in our history, from artificial limbs. And some of you might remember, that there are runners who have artificial limbs and things like that. So that kind of progression has been going on. I think the level you're asking, no, I don't think so. I think it's also one of these questions that does require us to think about things beyond what might traditionally be called science, because there's certain moral issues to this, right? Do we want to do that? Is that something that's good for us as human beings who think beyond science, who think about how we interact with each other, from philosophy to theology, all these sort of things, ethics? Yeah, I see that popping up. That's a big issue, and that requires a lot of specialties to come into play that extend, beyond what I do professionally. I have opinions about it, but they're similar to your own. So I would ask you, do you think that's a good idea? It's not one we're thinking about, as far as I know now.
Actually, there is a development in this area in astrobiology. I've recently listened to the talk by Susan Schneider,
Mm-hmm.
who works in that, and there is actually some development in this direction. So
okay, cool.
People do think about it.
Cool. Yeah, no, it's maybe it comes down to what one says superhuman means.
Thank you so much. I'm getting some reminders that it is well past 1.
Okay, no worries.
So, but
Thanks again.
Thank you so much again. And
anytime.
People say it's a wonderful lecture in chat. So
okay, good. I'm glad you enjoyed it. Yeah, if you have a link to it, and then I can link in the images if people want.
Yes, definitely. I would appreciate if you send me the
Okay.
link. I'll share it with everyone.
Thanks. All right.
Okay.
See you all. Have a good day.
Thank you so much. Goodbye, everyone. Thank you. Thank you for coming.